The regulation of population growth. There are many factors that affect population growth, and I want to talk about them as this presentation continues. The first thing I want you to keep in mind is that the concept that a population's growth is limited is a fundamental principle in ecology. In other words, ecologists believe that the populations of various organisms do not continuously increase forever and ever, but there are limited resources, which results in limited population. This is linked to Darwin's theory of natural selection, in which each individual has a high potential reproductive rate and can produce, in essence, excess individual offspring. And eventually the scarcity of resources limits the population so that competition becomes intense and the inherent differences among individuals become important as a source of natural selection, adaptation, and ultimately evolution. So these two concepts of population growth and natural selection go hand in hand. Now, I just said that populations do not continue to increase indefinitely. In other words, that there are limits. But I want to take a moment and sort of argue the other side and look at a condition in which there is the absence of resource limitations. Here we have a differential equation. dn dt is equal to r times n. That's the change in number, dn, over the change in time, dt, is equal to r times n, which is the population size. I want to focus on r for a second. R is what is referred to as the intrinsic rate of growth. It's also sometimes called the biotic potential of a population. And what r is as shown in the second equation, is the summary of things that cause the population to increase, that is, things that add numbers to a population, minus the things that subtract numbers from a population. In other words, R is equal to the quantity B plus I, where B is births and I are immigrations. And so we have births plus individuals moving into a population. So they're the things that add to the population. And we subtract from that the quantity D plus E, which is deaths, plus emigrations, individuals leaving the population. So if we look at the births plus emigrations and the deaths plus emigrations, and we look at the difference between those two, that gives us the biotic potential or intrinsic rate of growth of a population. If we were to plot that, dn dt equals r times n, in a way that we would display here, of time versus population size, we would get what is known as a J-shaped curve, or the exponential growth curve. This is unrestricted growth. This is growth in which the growth rate of the population accelerates, and the population is growing at its full biotic potential without limits. Now, as I said, that's not possible because there are going to be factors that do in fact impinge upon that population growth. So now let's bring it back to reality a little bit. Such things as drought, disease, food abundance, and parasites can affect the population's ultimate density or growth rate. That can be through mortality or reproduction, that is, adding individuals to a population, adding individuals to a population, or mortality, the deaths that occur in a population. So we have those two characteristics I talked about before. Right now we're sort of ignoring immigration and emigration, but we could add those in as well. The idea here is that these factors, drought, disease, food abundance, etc., can affect either mortality or reproduction or both, and as a result will affect the density and therefore the size of a population. What are the kinds of factors that affect population growth? Well, we divide them into two categories, abiotic and biotic. Abiotic factors being those that are physical, such as pH or temperature or humidity. And biotic, which as you can see listed here, are predation, food supply, competitors, parasites, pathogens, mutualistic relationships, etc. So biotic factors are biological factors, the interaction of one set of organisms with another, whereas abiotic are interactions with the physical world. Let's talk a little bit more about these biotic factors. The biotic factors, and to some extent abiotic factors too, but biotic factors can affect a population in really sort of two fashions. One from what's referred to as a top-down condition, and one from a bottom-up. And let me explain that. Now, in order to understand this, we have to think about a food chain or trophic structure. And I know we haven't spoken about it, but I think many of you have a sort of basic idea of what a food chain is. And imagine with me for a moment that we have an ecosystem in which there's grass, and then that grass is eaten by grasshoppers, and then those grasshoppers are eaten by birds, and then those birds are eaten by snakes. So we have a simple food chain, grass to grasshopper to bird to snake. Now let's just use that as a simple, very, very simple food chain. If we had predation, for instance, let's focus on the grasshopper population, for instance. If we looked at the grasshopper population and talked about the predation of grasshoppers by birds, because the birds are higher up on the food chain, that's referred to as top-down, as a top-down factor in affecting a population. It's coming from the upper levels of the trophic structure or food chain. On the other hand, if we saw changes in the growth of the grass, more abundant species or more succulent grasses to provide more food for the grasshoppers, that would be a bottom-up control or impact on the population of grasshoppers. So you see, we can talk about factors coming from top down or bottom up based upon the food chain or the trophic structure of a population. Let me give you an example of bottom-up factors by using the Galapagos penguins as an example and how their population is driven by El Niño cycles. Now remember, the bottom-up factors are those that affect the population from lower trophic levels. And what we need to stop here before we go any further is envision the food chain. That is, we have nutrients in the ocean waters that are used by marine algae and zooplankton as a food source. And then those zooplankton and algae are eaten by crustaceans and fish and other organisms. And those crustaceans and fish and other organisms are used as food by the Galapagos penguins. So, during an El Niño situation, the easterly winds push warm water across the Pacific and sort of pile it up against the coast of South America and the Galapagos Islands. As a result, the cold, nutrient-rich water, which is normally present in these areas, is replaced with warm water that has fewer nutrients. Ah, there you go. Fewer nutrients means less growth of algae and zooplankton. Less zooplankton and algae mean less food for the crustaceans and fishes and other organisms. Less fishes and crustaceans and other organisms means less food for the Galapagos penguin. You've got the idea. So, as a result of the marine food chain collapse, the penguin population declines. And as you can see here, as documented by these authors, we see a precipitous decline in Galapagos penguin populations during the El Niño that occurred in the early 80s. Therefore, we see a bottom-up impact on this population. If a factor is going to impact population in a way that it can actually somehow effectively control that population, it must do so in what's referred to as a density-dependent fashion. The effects of density-dependent factors increase in intensity as the population increases. In other words, at high population density, the density-dependent factor is more dramatically felt by the population, and at low densities, the density-dependent factor is less important or poses less of a threat to the population. That's density dependence, changes with density, as the term would suggest. Now, this can either be bottom up or top down. That doesn't matter, and it can either affect reproduction or mortality. Again, doesn't matter, but it's going to impact in a density dependent way. Well, if we have density dependent factors, that is, factors whose impact changes with the numbers, with the density of the population, then we need to modify our population growth equation. If you remember, we had dn dt is equal to r times n, the exponential growth curve. Well, now we still have that. Okay, we still have that, as you can see here. There's the r times n, but we've added here what's called an environmental resistance factor. This is a part of the equation that tries to take into effect the density-dependent factors that might influence population growth. Look at it for a moment. Think of a K, by the way, being carrying capacity, the largest number of individuals a particular environment can sustain. So that's its carrying capacity. N is the number of individuals. What I want you to see here is that if we think of a carrying capacity, a population with a huge carrying capacity, let's say 1 million is its carrying capacity. The environment can hold 1 million of the individuals. If we start with 1 or 2, let's say 2 individuals. If we were to look at this equation in that way, we would see that K would be 1 million, huge number, and N is 2, just a very small number. In essence, it's, practically 1 million divided by 1 million. You see the carrying capacity, because N is so small, it's insignificant. As a result, this environmental resistance factor is equal to 1. 1 times this is exponential growth. Now, the population continues to grow. N becomes equal to, or almost equal to K. Let's say it's equal to K. At that point, this becomes 0, right? 1 million minus 1 million is a 0. Divided by 1 million is a 0. So 0 times this factor is 0. The population stops growing when it reaches carrying capacity. So at low population densities, the population will grow and increase. As it reaches carrying capacity, the growth rate will begin to decline. Now, this will result in what's referred to as logistic growth, and will give us a curve that looks something like this. That is, where you have an increase, and then the rate declines till it matches, the density slows. I'm having a hard time saying that. The rate of growth slows until the population size reaches carrying capacity. This is a sigmoid curve and is sort of characteristic of a logistic growth. Not overly realistic, but much more realistic than exponential growth. Notice that we can talk about a lag phase in this population, an exponential growth phase, a deceleration phase, and then a sort of equilibrium phase. And typically in populations, there will be this sort of wavy condition. That is, it's not this smooth. This is what happens, predicted by this differential equation. But in natural populations, there's usually some fluctuation. The logistic population growth that we just described by that equation has some characteristics that I want you to keep in mind. First of all, if N, that is the number of individuals, remember that N means the population size and K is carrying capacity. So if N is greater than K, then this change in number over change in time, dN dt, is negative, right? Because the size is greater. The population is exceeding its carrying capacity. As a result, the change will be negative and the population will decline. That's what's shown here. The population will be driven down. If N is less than K, that is, if the number of individuals in the population is below carrying capacity, then the dN dt is positive and the population will be increasing. And finally, if N equals K, then the change in the population is 0 and the population will be stable. These are 3 sort of outcomes of that logistic equation that you need to be aware of. Keep in mind that the logistic equation takes into account the carrying capacity of a population, and that carrying capacity is based upon environmental resistance, that is factors, and you can see in this diagram, such as decreasing oxygen supply, low food supply, disease, predators, limited space, all of which will keep the population down, keep the density of the population down and hold it at its carrying capacity. Density-dependent factors typically act as a negative feedback in systems. That is, as population increases, they will have negative impacts on mortality, or positive impacts on mortality, that is, increased mortality and decreased reproduction. If a population decreases, then these density-dependent factors will cause reproduction to increase and mortality to decrease. Density-dependent factors can typically be identified by the correlation between mortality or reproduction and population density. These graphs sort of show that. Here's population density in each case, and on this axis is either birth rate or death rate. Here we have a population that is controlled in a density-dependent factor by both birth, by their impacts on birth and death rates. Let me explain that. Here, this line is the density-dependent death rate. As population density increases, the density-dependent death rate goes up. As population increases, the density-dependent birth rate declines. So both factors, birth rate and death rate, are affected by density-dependent factors. That's possible. It's also possible to have a population in which the death rate is not affected by a density-dependent factor, but the birth rate is. Here, the birth rate declines as population density goes up, and the death rate is not affected. Here's the opposite. The birth rate is unaffected by population density, but the death rate increases. So we have sort of three different conditions where both birth and death rates are affected, only birth rates, only death rates. But in a density-dependent fashion, and they have the potential to limit population growth. Density-independent factors are those which do not change with population size and are typically abiotic factors, such as pH, weather, fire, floods. They don't impact the population in a density-dependent factor. They simply cause some type of an unpredictable disaster. And as shown in here on this graph, as population density increases, mortality or reproduction is not affected in any density-dependent way. So let's summarize this. Density-dependent factors are, at least have the potential to regulate population size and growth. They will be best described by dn dt equals r times n times the quantity k minus n divided by k, where the carrying capacity is important. Density-independent factors generally represent a disturbance or a calamity that takes place. They may prevent the population from reaching the carrying capacity or equilibrium, but they do not operate, by definition, do not operate in a density-dependent fashion. Take-home points. No population can grow indefinitely. Several important regulatory factors comprise paired mechanisms that can limit population growth. That is, both abiotic and biotic factors can work together, top-down and bottom-up factors can work together, and density-dependent and density-independent factors can also work together. They can work alone or together. They can work on birth rates or death rates, or both, as we've seen. Now, population stability is something that we want to talk about. That is, do populations really reach an equilibrium and stay there? A stable population in the natural world is usually one that sort of fluctuates within relatively narrow limits. This is often achieved by both density and density-dependent and density-independent regulatory factors which work to regulate the size of a population. All populations usually fluctuate to some varying degree, And any stability that you see in a population is usually fairly short-lived in the natural world. Density-dependent factors tend to limit the degree of population fluctuation, but do not necessarily lead to stability per se. Most populations are regulated by a number of interacting factors, top-down, bottom-up, density-dependent, density-independent, as I've said before. Over time, the importance of regulatory factors may change. Therefore, long-term studies are important for understanding the process of population regulation, and it's not likely that any single one factor will regulate a population. Finally, I want to mention that we really need to think about populations as they relate to the landscape, as they relate to the larger area in which we find a species growing and thriving. A metapopulation is the term that's used for that. A metapopulation is a group of populations in a landscape comprised of habitat of varying quality, but these habitats are linked by migration into a regional group of connected populations of that species. So we have population centers of a species, and then they are connected by some kind of more or less regular migration that takes place to allow them to share the gene pool. And any given habitat patch is vulnerable to hard times and possible extinction, but the overall metapopulation will be comparatively stable because it's comprised of a sort of set of populations that fluctuate independently. So while these guys may not be doing so well, these guys might be thriving. Overall, the population remains more or less at a sort of stable condition, but individual populations may ebb and flow. This is an important concept, especially if you start talking about species conservation. The relationship between population size, distance, reproduction, and gene exchange is important because, as we see here, in a healthy population, we want reproduction, good exchange between populations. But as the population decreases in size, the reproduction is declining, there'll be fewer individuals in the gene pool. If we increase the distance between these populations, this is all the metapopulation, these are the individual component populations. If we increase the distance between populations, there'll be little reproduction, or actually probably poor exchange between the individual populations, and that can cause problems as far as the gene pool goes. So for a healthy metapopulation, we need to have high reproduction and good exchange among the populations that make up or comprise that metapopulation. Here's a model that looks at sort of the general concepts of population regulation and control. When we think of population size, we know that there are a couple things that can affect that. Birth and death rates, immigration and emigration. We know that predation and other things from top down, food resources and other things from the bottom up can control population size, that abiotic factors such as disturbance factors such as fire, storm, flood, cold snap, that sort of thing. Climate and weather can certainly affect this population as well. All this together will impact the population size. As take-home points, regulatory factors vary over space. Thus, populations are spatial mosaics of different regulatory processes. The megapopulation, the metapopulation. The metapopulation concept incorporates this spatial variation. The populations that comprise a metapopulation fluctuate and are regulated independently. However, they are potentially connected by dispersal among populations and that gene exchange that would occur.